Okay, we will continue our video. So for now, we are done in checking the analysis or checking the seismic drift, wind drift, vertical and horizontal regularities check. Okay, so now we will go to design of columns. Next, the design of beams, and design of shear wall, and design of foundation. Okay, so for the design of columns, so for number 51, design of columns, we will utilize this load combination. Okay, so we have here, this is the equation from NECP, and this is our load combination to use. Okay, so we already input that in the define of load cases and load combinations. Then this is for the first three is for dead load and live load. So basically that is gravity load combo. So dead load, superimposed dead load, reducible live, and live load. Also we have here R of live. So then the next is we have here gravity plus wind. Okay, then the next is gravity plus wind again. But for now, this is the lower limit of the load combo with the wind because it's just using dead load and wind. And here, dead load, live load, and wind. Okay. Next, for the strength design load combo, so in designing columns, we are dealing with the strength design. So all of these load combo are strength, okay, or ultimate. Now for the earthquake, we have response spectrum, SRSS. We have here this U8. We have here dead load and SDL. So basically, this is 1.2 plus 0.5 CAID. So this is the CA. So this is just basically I already explained it. 1.2 plus 0.5 CA times I times dead load. So you have your CA equivalent of 0.462. Then your I is 1.0 and the dead load is, you have dead load here, you have dead load here. So this is your dead load. So this is just the scale factor. Okay. Then reducible live, and then RSA is RSS as defined in the load cases. We have positive and we have negative. Okay. This is for the, basically this is for upper bound, or it will give you higher axial and compared to this one. So the other one is, this one is 0.9 minus 0.5 CAID plus response spectrum. This SRSS having acceleration U1 and U2 as defined in the load cases. Okay. Then we also have defined the load combination using RSX and RSY. This RSX is having a U1 alone and the RSY is U2. Okay. So they are with the different load cases. Okay. By doing so, we will input this one, and in our model, we already input that one, define load combinations, or that is also in load combination Excel. Okay. So in our load combination Excel, this one, we will using this one, U8. We will using this one for the design, and also this one, okay? So, this load combination, this is for static having a orthogonal effect. So, this is not applicable to this video. So, we have this load combo, this one, okay? Next, we will go here. Okay, so we will just close this one. And we will have these load combinations. Okay. So we have U1 up to U6. And also we have U8 up to U10. Okay. Now, we will select design combinations for the design. So basically, I'm here in the design phase, design, concrete frame design, and I will select the design combination. So for the design combination, so like what we have discussed, we will just select this load combination. Okay, this is having only the gravity, wind, and dynamic cases. Okay, so I will just cancel that one because I already put it here. So for example, you have here a blank. You don't have any design load combinations here, so it's leave with a blank. So you will just put the usable load combinations. Okay. So this other load combinations is for allowable. This is for the checking of pile reaction or number of piles. Okay. So we will leave the load combinations having static cases. Okay. So let's just click OK. Then I will just run this. Okay. So, but before I run that one, I will just show what is the column sizes here. So from base, I'm in the ground floor. I want to show it with the section properties. That is why I know it by using color coding. Then I will just show the Model Explorer. Then from Model Explorer, I can have my frame color code. So for now, I have C3. So I will just right click here, then modify. So this is color yellow. So this one, C3 850 by 850. And then I have 40 longitudinal bars and diameter 32. That is 4.5%. That is located here. Okay. So I just put the diameter 40 number of bars, longitudinal bars, equivalent to 40. So if you count this one, this is equivalent to 40. Then the diameter is 32, and it will give me a AS over BD or rho that is equivalent to 4.5. Okay, so this one for our checking, this is just a let's say we have here cover, and this is the number along 3 and along 2. This will give you 40 pieces. Then you have here the diameter. Then you have here the confinement. But for the confinement, we just check it using a ductility requirements from the code. Okay, so it will not matter for the ETABS, this value. Okay, if you are in SMRF or in ductility frames, you have to check these confinement bars using the ductility requirements. How many number of legs you will put here, what is the requirements, and along this direction, what is the requirements. Okay, so the requirements for that is from this code from the ACI and NSCP. So suppose you have here ties at this direction, then you will have here the calculations using this equation. Okay, for the F prime of C less than 70 megapascals. Okay, so we have these calculations here. ASH, our interest is to find the ASH. That ASH is the total area of these cross-sectional legs. This is 3 legs, and that the total area of that is this value, the ASH. So how to compute that one? We have here a ASH, and we have here the S or the spacing, and your BC, this is your BC. If you are considering this force, you will getting this BC, and you have S, that is the spacing of the ties perpendicular to you for this one. For example, I will just section this one. So this is the spacing. That is the spacing. Okay. So the spacing of ties. So you have that value. You have this 2 value. Let's say for the spacing, you have 100, and for the BC, you have a value, and you have a value of AG. This is equivalent to just the section, gross section, and you have the ACH. This is equivalent to the value of this section minus concrete cover, that is 40 plus 40. So that is the dimension minus concrete cover, 80 mm, and you have F prime of C, and you have FYT. So the FYT is basically the tensile strength of this ties. Okay, so now you will getting this value easily. Okay, so for example, we have here C3. I have the C3. I have C3, and I have B and H. I have this one, and I have this one, 77,000 psi, and I have Fy, I have Fyt, and I have main bar diameter and hoops. This is the ties. So you will getting this ASH2 and ASH3. So that is ASH3 at this direction, and this is ASH2 at that direction. Okay, so this is the value of ASH. Now, this value of ASH divided by the bar diameter, or the area of this bar diameter. Let's say you have 12 mm, that is equivalent to 113 mm squared, 113 mm squared. So you have 552 mm squared divided by the area of this one, of the 12 mm. It will give you 5 legs. Okay, so 552 divided 113, it will give you 5 legs. So at that direction of the force, you have 5 requirements, and at the perpendicular, you have 6 requirements. This is the number of legs. Okay, so that is why we have here ductility check, and the ETABS will just give you AB over S, not checking the ductility check of the confinement reinforcement. Okay, you have to do it manually. For the most of the programs is programmed like that. They don't give you the values for the ASH. Okay, so for this column, our interest is we will just put here 850 by 850. So let's say I have this value. So let's say C3, let's say 850 by 850. Then your F prime of C is 7,000, this one. Then you have there 7,000. Then 414, then you have here 32. Then you have here, let's say, we have for the 12 mm, if you use 12 mm, you will now get this value. Okay, and then 6 number of legs along x and y direction, or along 2 and 3. So you have here, basically you have here outer ties. Okay, then you will have another 1 2 3. So 1 2 3 4 5, you will have this legs. Okay, then for along perpendicular direction, you will be having this 4. So this is how you put the lateral ties or the confinement. So for the high-rises building, even though it's just the 12 mm is enough, but for the LO zone, they are using 16 mm. And for example, I have a column. We have this LO at the top and at the bottom. They use here 16 mm, and at this above LO, they are using 12 mm. Okay, so that value is, so that is in our, so it's not included here, but basically that is included here in the manual. So for your LO, so this one, there is a confinement zone here required by the code. You have to put here ASH at that zone. So the practice of other designers, they just put 16 mm diameter here, and at this zone they are just using 12 mm, because even though the 12 mm is enough, so they just want to have a factor of safety. Okay, so that value is this. So transverse reinforcement from ASCE and from NSCP. So this is the code. Okay, 418.7.5. Okay, so now going back to the software, we have here longitudinal bar. This is to be checked. The section is to be checked. We will run the section and we will study if this section is enough. Okay, so this is to be checked. Next, I will just click OK. Then I will just click run. Okay. if we are dealing with the column to be checked, we are after to check the demand capacity ratio. So if the demand capacity ratio is greater than 1, it's just saying that your column is undersized or under-reinforced. But for our case, our enforcement is already 4.5%, so we don't have we have to precise if the demand capacity ratio is exceeded. Okay. Or we can add the reinforcement for in case you have 1% of longitudinal reinforcement and your demand capacity ratio exceed, let's say you're getting 1.2 or 1.5 demand capacity ratio with that with reinforcement 1%, you have to increase the reinforcement. You will make it 2%, and if it will pass, it's okay. That's it. And if will not, you can do iteration. So for this time, the red color indicates that there is a failure. Okay, for example, I will get this value. I will get this column. I will just select it, select all story, and then I will just select it and right click, show selected objects only, 3D. So I am dealing with one column only. The rest you will do it by yourself. I will just investigate it here. Then I will apply this one. So column PMM interaction ratio. You will notice there that this is red color and it will indicate that this is a failure. So for this PMM interaction ratio or the DCR ratio, so we have this column. So meaning our column is undersized, but you can make it 4.5. You can make it 6 from the code. But as a designer, I am also considering the construction status, or this is very congested, and if you have splicing zone 30% or 1/3, at that level you splice the 1/3 of the reinforcement, and at that section you will now getting 6%. So for this time you will make it 900 by 900. I think you can reiterate this by 900 by 900, or you and maintain the 4.5% if you are maintaining the area of the rooms. Or the other trade want to have a smaller column, but if in this case we have to put, or we have to add a little bit dimension. So let's say we have here 1 meter by 1 meter, and for your practice you will just modify this one and rerun it, and you have to review or study what is the ratio of this. Okay, so for now this column is undersized. Let me do it. So let's say this is 850 by 850. I will make it 1 meter by 1 meter. Let's say 1 meter, because our building is irregular. Then I will just put here 1 meter by 1 meter. Then I will just let the number of bars as is, but basically the row will become different, but just for the reiteration. Now you will find out in this run, you can just select this column alone, but sometimes for this program, the column interaction, PMM interaction is sometimes cannot be calculated if you just select column alone. So it gives you higher this ratio. So meaning your rebar decrease because you increase the section, and rebar percentage, you can check that one. You have 3.22, and now if you have 3.22, you can put additional bars. Let's say we will jack it up to 4%. Okay, let's say I have 4% now. So let's say I will just 1 meter. Let's say I will have here 14 by 14, 32. Let's just click OK. But before you proceed to the next element, you have to correct these section names to match with the definition inside, to avoid any problems or any. Okay, so it's failing again. So this is 4% and it's failing. So 1.22. So okay, you can also put a so you can bundle this rebar. You can bundle that one. Okay, so I will just input a higher value. You can bundle that one, but you have to maintain the rebar percentage to avoid congestion. You have and to follow the code restrictions. It's failed again, and it's 1.022. And if you notice the rebar percentage, you're getting 6%. So in this case, you don't have a splicing in this zone, but that is not recommended to design like that. So we'll just maybe because of the second of this floor is longer, that is why it's failing. The short column length is failing. Okay, so I will just assign this value, and I will just assign the section, and I will reduce it. Okay, so it's closer to, so above 1, you are failing. So you can just add a 2 pieces of rebar or one 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 piece of rebar at every corner to avoid that DCR greater than 1. So I will just put here 16 and there is 16. So this is the iteration process for the design. You will be doing this for all of the column, but you have to group the column. So we will put the groupings of the column. Let's say, for example, you have here okay, so this ratio is acceptable, 0.99. But in this case, you can also increase the size to have a factor of safety. Increase the size and let's say 1.1 by 1.1 to avoid the congestion of the concrete or avoid the congestion of the rebar. And the concrete may not be passed through the rebar. So in this case, for these projects, for like this project, and this is 7,000 psi, some designer or contractor requires the concrete that is self-consolidating concrete. So there is no slump test, there is a spread test to do. Okay, to avoid or to make sure the quality of the construction. Okay, so this is the how we deal with the column. So for all of the columns, you have to set let's say all of this column, you can make it one section so that you can be for simplicity of iteration. Okay, so in this case, all of the column here is pass, but the other is failed. So you have to do it by yourself. You have to add the rebar at a section. You iterate this one to make it pass. Okay, so this is in the end of the video.